Hi, welcome to the Easy Learning session. Let's dive into today's topic. Are you ready? Today we are going to learn Chapter 1, Force. In this chapter, you will get to understand the concepts of types of motion, moment, couple, and equilibrium of bodies. Types of motion. In physics, we can broadly classify motion into two main categories: linear, or translational motion, and rotational motion. Let's break them down. First, let's look at linear motion. Imagine you have a rigid body that is completely free to move. When you apply a force to this body, it starts to move in a straight path, directly in the direction of that force. This straight line movement is called linear motion. A perfect everyday example of this is simply pushing a box across the floor. Next, we have rotational motion. This happens when the rigid body is not entirely free to move, but is instead pivoted at a specific point. If you apply a force to it now, it won't slide away. Instead, it will rotate around an axis that passes right through that pivot point. For example, think of a wheel pivoted right at its center. If you apply a force tangentially along its outer rim, the wheel stays in one place, but rotates smoothly about its center. Now that we understand how force causes a pivoted object to spin, let's talk about the actual turning effect itself, which we call the moment of a force, or torque. Let's look closely at a pivoted, rotating body. What actually decides how easily that object will turn? It depends entirely on two major factors. First, it depends on the magnitude of the force applied. Second, it depends on the distance from the pivot point to the line where the force is acting. If you multiply these two factors together, the force and the perpendicular distance, you get the mathematical value for the moment of force, or torque. This product is the exact mathematical reason why things rotate. To measure it accurately, just remember this simple formula. The moment of a force equals the magnitude of the force multiplied by the perpendicular distance from the axis of rotation to the line of action of the force. If you look at a typical diagram, if your force is F and the perpendicular distance from the pivot point O to that force line is OP, then your torque is simply F multiplied by OP. If you want to get the absolute maximum turning effect out of a force, you need to apply that force as far away from the pivot point as possible. By maximizing that perpendicular distance, even a small push can create massive torque to turn the body easily. This is exactly why door handles are always placed at the edge of a door, far away from the hinges. Now, let's talk about units. Since torque is force multiplied by distance, its unit is simply the unit of force multiplied by the unit of distance. In the SI system, force is measured in newtons and distance in meters. So the SI unit of moment of force is the Newton meter, which we write as Nm. In the smaller CGS system, force is measured in dynes and distance in centimeters, giving us the unit dyne centimeter. Sometimes you will see force measured in gravitational units. In that case, the SI unit becomes kilogram force meter, or kgfm, and the CGS unit becomes gram force centimeter, or GFCM. To ace your numerical problems, you absolutely must memorize how these units connect to each other. 1 Newton meter is equal to 10 to the power of 7 dyne centimeters. If you need to convert gravitational units, 1 kilogram force meter is equal to 9.8 Newton meters, and 1 GF force centimeter is equal to 980 dyne centimeters. Now that we know how to calculate torque and convert its units, let's talk about its direction. The moment of force is a vector quantity, which means it has both a value and a specific direction in space. If you look at the axis of rotation, an anti-clockwise moment is directed along the axis outwards, while a clockwise moment is directed along the axis inwards. To easily visualize this three-dimensional direction, we use a classic physics trick called the right-hand thumb rule. Imagine curling the fingers of your right hand in the exact direction that the object is rotating. If the body is turning anti-clockwise, curl your fingers anti-clockwise. Your thumb will naturally point straight up and out of the page, confirming that an anti-clockwise moment is directed outwards. Now try it for a clockwise rotation. Curl your right fingers in the direction of the clock hands. Your thumb will automatically point straight down into the page, showing you that a clockwise moment is directed inwards. Your thumb acts as the vector arrow, pointing exactly where the torque is directed along the axis of rotation. Because direction matters so much, physics has a strict rule for sign conventions that you must follow in your numerical problems. If a force causes a body to turn in an anti-clockwise direction, we call it an anti-clockwise moment, and it is always taken as positive. On the other hand, if the force turns the body clockwise, we call it a clockwise moment, and it is always taken as negative. Remembering that anti-clockwise is positive and clockwise is negative is important to solving balancing problems later in this chapter. So, what actually determines which way a pivoted object will spin? It comes down to two simple things: the point where you apply the force and the direction of the force itself. Let's look at how changing the point of application changes everything. Imagine a flat disk pivoted right at its center. If you apply a force pushing right at the bottom edge at point A, the disk spins anti-clockwise, giving you a positive moment. But if you keep the force pointing the exact same way and apply it at the top edge at point B instead, the disk suddenly spins clockwise, giving you a negative moment. The same result can also be achieved by just changing the direction of force at point A. By simply changing where you push or which way you push, you completely flip the direction of the turning effect. Next up, let's explore a fascinating concept called a couple. Here is a little secret in physics that might surprise you. A single force acting on a pivoted body can never cause rotation all by itself. In reality, in a pivoted body, rotation is always produced by a pair of forces working together. If the body is not pivoted, it's a different scenario, and a single force can also produce rotation about the center of mass of the body, but that is not of our interest today. When you push a pivoted object, you are applying an external force. At the exact same time, an equal and opposite force of reaction is automatically produced right at the pivot point. Because this reaction force happens right at the pivot, its distance from the axis of rotation is zero, meaning its own turning effect is zero. That is why textbook diagrams usually don't show it, but it is always there. When you have two equal, opposite, and parallel forces that do not act along the same line of action, they form what we call a couple. You always need a couple to create a rotation. Think about opening a door. The rotation is actually caused by a couple consisting of two forces: the force you apply at the door handle and an equal and opposite reaction force acting right at the hinge. If you want a much larger turning effect, you can explicitly apply two forces that are equal in size but opposite in direction, ensuring they both work together to spin the body in the exact same direction. You see couples in action everywhere in daily life. Turning a water tap, tightening the cap on a bottle, turning a key inside a lock, winding up a mechanical watch, spinning a car's steering wheel, or even pushing the pedals on a bicycle. All of these rely on a pair of equal and opposite forces working together to create a smooth, rotating motion. Now, let's look at the math behind how a couple works. Imagine a straight metal bar, AB, that is pivoted right at its center point, O. Let's apply two equal and opposite forces, each of magnitude F, at the two ends, A and B. Because these two forces are completely equal in size, but opposite in direction, they cancel each other out horizontally and vertically. This means their total resultant force is 0, so the bar cannot slide or move in a straight line. But because they act at different points, they both pull and push the bar to turn it in the exact same direction. In this case, they both make the bar spin anti-clockwise. To calculate the total turning effect, we just find the sum of the moments created by each force individually. The moment of the force at end A is F multiplied by its distance to the pivot, OA. The moment of the force at end B is F multiplied by its distance to the pivot, OB. Both of these are turning the bar anti-clockwise. If we add them together to get the total moment of the couple, we get F times OA plus F times OB. By factoring out F, the equation becomes F multiplied by the sum of OA and OB. But looking at the bar, OA plus OB is just the total length of the bar AB. If we call this total distance between the two forces D, then our final formula is simply F multiplied by D. This distance D is a very important term in physics, known as the couple arm. So whenever you need to find the moment of a couple in your numerical problems, you don't need to calculate both sides separately. Just remember this golden formula. The moment of a couple equals either of the forces multiplied by the perpendicular distance between the two forces, or the couple arm. Now, let's move into our next major topic, the equilibrium of bodies. Up until now, we have learned that when a force acts on a body, it causes some kind of movement. It is also possible to apply two or more forces in such a way that they completely balance each other out. When this happens, the total resultant of all those forces combined equals 0. And the algebraic sum of all the individual moments about the fixed pivot point also equals 0. Because everything perfectly cancels out, these forces produce absolutely no change in the object's current state of rest, or in its linear or rotational motion. When this happens, the body is said to be in equilibrium. Broadly speaking, equilibrium comes in two different kinds: static equilibrium and dynamic equilibrium. Let's look at static equilibrium first. When an object remains completely at rest, even under the influence of several different forces, we say it is in static equilibrium. You see this happen all the time in daily life. Imagine a box sitting on a tabletop. If you pull it to the left with a certain force, and a friend pulls it to the right with the exact same amount of force along the same line, the box won't budge. The forces are equal and opposite, meaning there is 0 net horizontal force acting on it. Another great everyday example is a book simply resting on a desk. The Earth's gravity pulls the weight of the book vertically downwards. At the exact same time, the surface of the table pushes vertically upwards with an equal and opposite reaction force. Because these two forces cancel out, the book stays perfectly still. You even see static equilibrium in a classic beam balance scale when it sits perfectly horizontal. The clockwise turning effect caused by the object on the right pan is completely balanced out by the anti-clockwise turning effect from the weights on the left pan. Because the total moment is 0, the beam has no rotational motion and remains completely at rest. Now, let's explore the second type, which is dynamic equilibrium. This happens when an object stays in a constant state of motion, whether it is sliding in a straight line or spinning, even while several external forces are acting on it. A perfect example of this is a falling raindrop. As it falls to Earth, the downward pull of gravity is perfectly balanced by the upward push of air resistance and buoyancy. Because the net force on the drop becomes 0, it stops accelerating and falls at a perfectly steady, constant velocity. You also see this when an airplane flies at a constant height. where the upward lift generated by its wings exactly balances its downward weight. To summarize everything we have looked at so far, there are 2 mandatory conditions for equilibrium that you must memorize. First, the total resultant of all linear forces acting on the body must equal 0. Second, the algebraic sum of all the moments about the pivot point must be 0. This means the total anti-clockwise moments must perfectly balance out the total clockwise moments. This brings us straight to the principle of moments. According to the principle of moments, if a body is in a perfect state of equilibrium, the sum of all the anti-clockwise moments will always equal the sum of all the clockwise moments. To easily verify this principle in a physics lab, we can perform a simple experiment using a standard meter rule. Imagine suspending a meter rule horizontally from a fixed support using a strong thread tied right at its center point, O. Now, we suspend 2 different spring balances with slotted weights on either side of the thread. Let's call the weight on the right side W1, placed at a distance of L1 from the center, and the weight on the left side W2, placed at a distance of L2 from the center. If you look closely at how these weights pull on the rule, the weight W1 on the right side tends to turn the meter rule in a clockwise direction. Its clockwise moment about the center point O is calculated as W1 multiplied by L1. On the flip side, the weight W2 on the left side tries to turn the meter rule in an anti-clockwise direction. Its anti-clockwise moment about point O is calculated as W2 multiplied by L2. By adjusting the positions of these weights or changing the weights themselves, we can make the meter rule sit perfectly horizontal and balanced. In this state of equilibrium, if you measure the values, it is always found that W1 times L1 exactly equals W2 times L2. In plain English, the clockwise moment perfectly equals the anti-clockwise moment. This simple, elegant experiment completely verifies the principle of moments. With that, we have reached the end of the chapter. Now, to refresh what you learned, here is an interesting problem for you to solve. Imagine a uniform wooden plank that is exactly 6 meters long and pivoted right at its center point. On the left side, your friend Rohan, who weighs 40 kgf, is sitting at a distance of 2 meters from the pivot. Right next to him, at a distance of 3 meters from the pivot, which is the very edge of the plank, sits a heavy toolbox weighing 10 kgf. On the right side of the plank, your other friend, Priya, who weighs 55 kgf, wants to sit down to keep the plank perfectly horizontal and balanced. At what exact distance from the center pivot should Priya sit to achieve perfect equilibrium? So, pause the video, scratch your head a bit, and drop your final answer in the comments section below. I hope this video made learning a lot more fun for you. Make sure to hit that like button and share it with your classmates. Also, please subscribe to the channel so you don't miss the next video. Thank you so much for watching, and I will see you all next time. Bye!